All right, so let's look at some of the other things that change spin state.
Isn't the HOMO on oxygen going straight into and out of and straight up and down? It's not actually on the left or right face.
The HOMO is, what are the LUMOs?
Well, we only care about the
No,
HOMO for it to bond to.
you're saying that this pair is not sticking out of the end?
Right.
That is correct. Oxygen does not bond straight on. When oxygen bonds, we're going to get to this later, when oxygen bonds, it's at an angle. It's pointy end on. It's not straight on. So yeah, you have to look at the sigma, well, it's usually the HOMO of the ligand. You have to look at where those are to find out how it really bonds.
Well, it doesn't actually bond, like the oxygen bonds to something else on the protein, and then that brings the oxygen close, isn't it? So it's not really in the form of a dye. It's not a dimer that bonds it. It's already, it's getting attached by something else. So it's pi bond, isn't it? Not really like a pi bond. It has more of a negative character than it does pi bond, because it's already bonded.
The oxygen in hemoglobin?
Yeah, I thought it was bonded, like the protein bonds and that brings it in.
No, you're thinking of doming. The oxygen, you're thinking of the allosteric effect that comes from doming the iron. We're going to talk about that later. But oxygen is not being bound to something first and being brought into the iron position. Oxygen is going straight in. But when it does, there are four, in hemoglobin, there are four different hemes. When one bonds, it goes strong fill, low spin, and it domes. It changes the geometry of the iron slightly, puts some stress on the porphyrin ring, and that causes other irons to begin to dome. It feels some doming stress, which makes them bond their oxygens more easily. I think that's what you're thinking of. But I'm not aware that oxygen is interacting with some non-metal part of the protein and being brought in to the active site.
I sure there is like, when it attaches it sucks that. It pulls that iron this way, and you have another one.
That's the doming effect. And that's a consequence of the high spin, low spin shift. Yeah, that's a doming effect, and it's an allosteric effect. So when one bonds, the other ones bond more readily. But we'll talk about that in greater detail when we get to the very last chapter we're going to do, the inorganic chapter 16. We're going to deal with that. All right, so we have some options. If you look on page 378, we've got all the options. I think it's all of them. Does that start with D1? Okay, so they've left out the octahedral d-electron organizations for the ones that have no choice. So we've got the 0 state, the D1 state, the D2 state, and the D3 state that have no high spin, low spin options.
What page was it?
378. But when we get to D4, we begin to get an option. With D4, we have a high spin and a low spin state. High spin would look like that. Low spin would look like that. D5, D6, D7, we still have options. By the time we get to D8, we've lost our options. So D8, D9, in D10, we have only a single state, so we don't care really whether it's high spin or low spin. There is no option for high spin or low spin. We do, however, still care about delta O. But it's all those middle ones, D4 through D7. We do have an option of high spin or low spin. And we want to kind of set up some rules for figuring out if that's going to happen. The first rule we have is kind of a simplistic rule. It's on page 379, and it has to do simply with this, it has simply to do with the size of delta O versus pi c. So if we have some idea what, actually pi e works into that as well, if we have some idea what the distance of delta O is, and if we have an idea, you notice that between these pi e is not changing, but pi c is. So we've got one pi c. So here we have elevated one electron through delta O. Here we have added one pi c. The most simplistic way of looking at this is whichever one of those is lower, that's the one that's going to be favored. So if pi c is lower than this delta O value to raise the electron through that energy, then this one wins. If delta O is lower than the pi c value, then the high spin wins. The trouble, you got to know a whole lot of information to make that work. And pi c is really hard to figure out when the orbitals keep changing their size when you start bonding ligands around them. So it's too simplistic to work with. A better way to think about these energies is using what's called the ligand field stabilization energy. So here's how LSFE works. We begin with an assumption that the 3d electrons have some particular level, and when you make them split 3 down, 2 up, we split this one going down, it's 2/5 of the value of delta O, and this one going up 3/5 of the value of delta O. And what we can do is a very quick calculation. What is the total energy of however we've arranged the electrons? Every time an electron goes down to the T2G set, we're going to subtract 2/5 of delta O, and every time it goes up to the EG set, we're going to add 3/5 of a delta O. So let's compare, let's take the D5 as our example for calculating LSFE. There's the high spin case and the low spin case. So let's calculate how much total energy we're getting out when we put the electrons in, if they had all started at this middle point. So we have 3 electrons in the T2Gs, and each one of those will subtract 2/5 of the value of delta O. And we have 2 electrons in the EG set, and each one adds 3/5 of a delta O. So doing a little bit of math, no, that's not right. So 3/5, 15. Well, it's just 6/5, minus 6/5. plus six fifths.
Just
So,
right the first time.
because it's uniformly distributed, minus 6/5 of delta O plus 6/5 of delta O. There is no stabilization energy. By distributing the electrons evenly, the net energy has not gone down.
Where does that energy come from? Is there some radiation source that's supplying energy to the two that go up?
No, the energy would come from vibrational energy, and that's where it would go on formation. All right, Ligand-field stabilization energy of the low spin D5 state.
What would prevent these lower energy ones from gaining some of that vibrational energy and promoting to a higher energy level?
Nothing. But they wouldn't stay there. If the total energy of all the vibrations wasn't enough to create an inverted state, then they'll come right back down and release all the energy that they absorb. It happens all the time. It's why things are colored. So, color causes light hitting it causes an electron to pop up. It drops back down really fast. If it drops down slowly, then it phosphoresces, but it's only if it drops down and there's no vibrational pathway to get back down to the ground state. So yeah, it happens all the time. The electrons are jumping up and falling back down. So ligand field stabilization energy, we now have 5 electrons in the T2G, which is minus 2/5 of delta O, and here we end up with 2, or a negative 2 delta O, which means the low spin state is energetically favored. Now, here we have ignored the contribution of pi Cs. We don't know what it is, but we do know, just based on the configuration itself, minus 2 of whatever the value and energy of delta O is, that's how much energy we get for having the low spin D5 over the high spin D5, so this alone tells us the low spin D5 should be the favored state. However, we have also added, now we'll consider pi Cs. And here, if we add pi Cs, we have to add 2 pi Cs. Well, that says it is the high spin state, according to pi Cs, that is favored. Here we've had to push 2 electrons into the same orbital. But when we consider pi E's, how's it look? Remember the pi E formula? It goes back a ways.
And minus 1 over 2 times again.
Yeah, so it's so with the high spin, we have a set of 3. So 3 and 2, so that's 3 pi E's. And I'll subtract those out because they're negative. And we've also got a set of 2. So we've got a total of 4 pi E's. What do we have here in the low spin? So we've got 3 up-pointing electrons, which is 3 pi E's, and we have 2 down-pointing electrons, which is also subtracting 4 pi E's. So the pi E's in this case don't tell us anything. It's all a battle between the value of delta O and the value of pi C. That tells us which spin state would be expected. There's a chart on page 382 that lists